All right, so let's take a look at this here. And if I put in x squared into my limit definition, well, what do we have? The limit as h approaches 0 of, well, f at x plus h is going to be x plus h squared, then minus f at x, so minus x squared all over h. And of course, what we have, as we always have in a, right, somebody's trying to come in. Okay, what we always have in a limit definition is we have this indeterminate form, meaning the numerator and the denominator are both approaching 0. So who's the one who just came in? I think it was R1. Who just came into the class? Irvine.
Yeah, hi, it's me.
Okay.
I just came in a bit late.
Okay, I'll send your name in after there. I just took attendance. Okay.
Okay.
And so here, what we want to do to try to solve this limit is we need to do some algebra. So what's the obvious thing to do here? If I want to try to determine this limit, what's the only algebra that's really at my disposal? Any ideas people want to throw out? Yeah, expand the brackets. So there you go. Limit as h approaches 0 of x squared plus 2xh plus h squared minus h squared. And then some nice things start to happen because the x squareds start cancel out. And lo and behold, you can factor out an h in the numerator and denominator. Well, in the denominator, it's already factored out. And what are we left with in the numerator is we're left with 2x and then plus h. And of course, the h's cancel out. And we're just left with the limit of 2x plus h. And we say, well, 2x doesn't depend on h at all, so it doesn't change as h is approaching 0, but the h gets smaller and smaller and smaller, so this whole thing approaches 2x, okay? And so what we have is the derivative function for x squared is just equal to 2x, all right? And so the thing about doing this is, does this mean we have to do this every single time that we want to determine a derivative? Okay, because while we're very happy to not get an approximation for the rate of change, we're happy to have a derivative function, this is quite a bit of work. Okay, and so here, this is where hopefully you started to see a pattern. Okay, so of these two, do folks want me to do both of them, or are we okay is there one we can skip? So are there people who want me to do this second one?
Yes, please.
Okay, so let's do the second one. So now we're f prime at x, and similarly here, limit as h approaches 0. So now, okay, we have to input x plus h. So, there you go, x plus h squared. Again, plus 2 times, wherever I see an x, I input the x plus h. Okay, and this whole thing just represents f at x plus h for this second function. But now we need to subtract f at x. So we're subtracting x squared plus 2x. Okay, and all over h. All right, very nice. So now, guess what? I got to do this whole thing again. So what I'm hoping this is going to motivate you to want to learn is, might there be rules to taking derivatives that don't involve you having to always do this limit definitions? I'm going to go pretty quickly here because some of this stuff I've done before. So x squared plus 2xh plus h squared, and then we have plus 2x plus 2h, and then minus this thing. Make sure you're careful about your signs all over h. And look at what happens again. That x squared cancels out with the x squared, and this 2x cancels out the minus 2x. And all of a sudden, what is special about all the terms that are left over? Do you notice something similar to before? What is special about all the terms that are left over? Who can tell me? I got this one, I got this one, I got that one. What's special about all those terms?
You can factor out the h.
There you go. They all have a factor of h. So what am I left with here? I'm left with 2x. Okay. Then plus, well, I've got 1h left there. And here I just have plus 2. Okay. And lo and behold, the h's cancel out. And so now I can take the limit. So the 2x doesn't depend on h. So that h is approaching 0 doesn't affect the 2x. This just gets closer and closer to 0. And the 2 is a constant. So the limit of a constant is just the constant because 2 doesn't change as h approaches 0. And now we have our derivative function. Okay. But what we want to do here is we want to notice some patterns and look at what I have. Hey, I had the x squared here, the x squared there, and they seem to both produce the 2x. Okay. And now, if I look at this function, well, 2x is just a line. If I think of this function on its own, it's just the line y equals 2x. What can you tell me about the rate of change of this line? Where does one find the rate of change of a line?
Any value add on to 2?
Yeah, because 2 just represents the slope of this line. And of course, that's the nice thing about linear equations is that, the slope gives you the rate of change at all points. And look at that. 2 represents the slope of that line, meaning the derivative of that function. So this kind of gives us an idea that maybe there's some patterns. Can you see that the derivative of x squared is 2x based on what we found here? The derivative of 2x is just equal to 2 based on what we know about linear functions. And the derivative of the sum of x squared plus 2x looks to be the derivative, the sum of the individual derivatives. Okay, so let's try to write that down as a rule. Okay, what is that telling us? It's saying that if I'm taking the derivative of the sum of two functions, okay, see how I'm writing this more generally? Well, based on what this is showing, it seems to show that this is the same thing as taking the derivative of the individual functions and then adding them together. Because the derivative of x squared is 2x. That's what I have here. Derivative of 2x is 2. That's what I have here. So it's the derivative of the first function plus the derivative of the second function. Okay, so this is very nice. Okay, because as an example, let's say I was taking the derivative of e to the x plus sine x, two derivatives that you would have learned how to find in the last unit. You know how to take the derivative of e to the x. You know how to take the derivative of sine x. Now with this rule, how do I take the derivative of the sum? I just take the derivative of e to the x, and I can add it to the derivative of sine x. And these are two derivatives, simpler derivatives that I know how to take. Who's going to remind me, what's the derivative of e to the x? It's the easiest derivative of them are. That's right, e to the x, and then the derivative of sine x is just cos x, okay? And I can do this, work with the individual derivatives because of this law, okay? This is the sum rule for derivatives. Now, can you sort of see that it likely would have been a very similar scenario if I had a difference? Okay, it would look very similar if I had a difference. So here we can add to this rule. There you go. Okay. Now, what I want you to do is look at what I did here and see if you can work on x cubed. I'll give you a bit more time to work on x cubed, and then that's going to take us to the next law. Okay. So let me give you a bit of time to work on that, and I'm going to make the changes to the attendance. Okay. Give me just a minute. I'll leave you some time to work on that. Sorry, this is a message for Awan Parveen. I'm not seeing your name on the list. Might you go by another name or?
No, my name's supposed to be on there.
Okay. Because I see an Awan, but it's Awan Abbas.
Yeah, that's my middle name.
Oh,
Abbas
that's you.
Parveen.
Okay, great. Maybe when I copied and pasted in shop. Okay, great. All right, I've changed that. Okay, I'm just gonna. All right, so let's get. All right, let's get back to this here. So here we saw that when we looked at x squared plus 2x and we found the derivative, we saw that it ended up giving us the same answer as if we had taken the derivative of the first function, then the derivative of the second function, and added them together. Okay, but notice here how I asked you for x squared and it gave you 2x. Well, what happens when you do x cubed? So let's do, derivative of x cubed. All right, so that's the limit as h approaches 0 of f at x plus h. So I'm going to put x plus h into x cubed. So x plus h all cubed minus x cubed, because that's f at x here, all over h. And obviously this is a bit annoying because we have to expand x plus h cubed. All right. Now, if you know Pascal's triangle, you can do this way quicker, but let me do it the longer way. So I have x plus h, and I'll do x plus h squared. So x squared plus 2xh plus h squared. Okay. And then minus x cubed. Okay, so this is again why we really want to see if we can find some derivative rules that don't force us to do this every time. So x times x squared, x cubed. So what do we have? We have 2x squared h, okay, plus x squared h. So that's going to be 3x squared h. Okay, now we have 2xh squared. Okay, this one here, plus another xh squared in that multiplication. So plus 3xh squared. And then the last one we haven't done is h times h squared is h cubed. Oops, plus h cubed. And hey, look at that. Doesn't calculus work out really nicely because the x cubes cancel out and everything else has h's in it. So we factor it out. So we're left with 3x squared. And then here, what are we left with? 3x, but there's an h left over. And then here we've got a couple of h's left over. Cancel that out. And now we can take the limit. So here, 3x squared doesn't change as h gets closer to 0. This, though, whatever 3x is, it's being multiplied by h, and h is getting closer and closer to 0. So this whole expression is just going to be approaching 0. And what's happening to h squared as h approaches 0? Hey, it's also approaching 0. And what are we left with? 3x squared. Okay? And this is where we start to notice something very interesting. That when I took the derivative of x squared, I got 2x. When I took the derivative of x cubed, I got 3x squared. Okay. Now, I think some of you already knew this rule. And, well, what seems to be the pattern here? What seems to be happening to the exponent in my power of x? What happens to that power when I take the derivative? Here, x squared. Look where the power ends up. Yeah.
Getting one number down.
There you go. It becomes the coefficient, the number that multiplies. Here, when I took the derivative of x cubed, look at where the 3 ended up. It ended up becoming your coefficient. And somebody else noticed something that, hey, what happens to the power? The power went from power 2 to power 1. The power 3 became power 2. Okay? Now, I don't have time in this, in sort of this session to prove this formula. The same thing here. We could actually do a proof to show that this is true, but we're going to use examples to demonstrate that it's a reasonable rule. And it looks like we just found a nice rule here that the derivative of x to some power, well, the power becomes the coefficient, and what happened to the exponent? It goes down by 1. Okay? And here we have the sum and difference rule. This is what we call the power rule. So it gives you the derivative of any power function. X to any power becomes this here. Okay? And this, of course, is very, very powerful because, hey, what are polynomials made up of? They're made up of powers of x. What are rational functions made up of? They're made up of powers of x. Even if you take something like the derivative of, say, root x, how can I rewrite root x? Who's going to tell me? How can I rewrite the expression root x? Any takers here? Anybody remember how you can rewrite the square root of x?
X to the power of 1/2.
There you go. So it becomes x to the power of 1/2. And now with this rule, I can find the derivative even of some root functions, because that, as somebody brought up, well, hey, the exponent becomes the coefficient, and then what's 1/2 minus 1? Negative 1/2. So this just becomes 1/2. This goes to the denominator. There you go. And you can find this derivative. All right. So now, so far, we have the sum rule, the difference rule, and now we have the power rule. But there's one other thing that you find in polynomials. Okay. You also find coefficients. Okay. So I want to take a look at this example that we talked about there, that we said the derivative of 2x, we reasoned out, should be equal to 2, because y equals 2x is just a line, and that's the slope. And of course, we know the slope is equal to the rate of change. So the derivative of this function, which of course we know represents the rate of change, is just always going to be equal to 2. Okay? But now, let me think of this coefficient here and think of this. What if I have just the derivative of x? What would that derivative be equal to? What is the slope of this function? Nice and easy. Yeah, it's just equal to 1 because the slope of this function is 1, and it's always, the rate of change is always 1, meaning that the derivative of x is equal to 1. And this kind of leads us to a third rule, okay? That here, when I just have a coefficient in front, what effect does it have on the derivative? Well, it has no effect on the derivative. I can rewrite this as 2 times the derivative of x. So 2 times, what's the derivative of x? Well, it's just 1. And there we go. We get the correct answer. And so this now gives us a third rule that we can use. It's what we call the constant multiple rule. So if I have the derivative of any constant, so c is just some number times a function, okay, that's the same as taking that constant and multiplying by the derivative of the function. Okay? And this now gives us our third derivative rule. And what's nice now about this third derivative rule is we can determine, or we're going to see in a second, we can determine the derivative of any polynomial. So I see that there was a hand up. Who had their hand up? Oh, Jalen? Sorry, Jalen, I see your hand up. Okay, well, anyways, if you have a question, you can maybe put it in the chat or just open up your mic. All right. So let's rewrite these rules. Let's rewrite these rules. So we have them. Would be a good idea for you to have them down. So here we'll start a list of our derivative rules. Okay. And the first one I'll actually write down is going to be the power rule. Okay. Which says that the derivative of any power of x is equal to that power times x to the power minus 1, the original power minus 1. Then we have the sum and difference rule. Okay, and what that says is that if I take the derivative of the sum or difference, so, since it's a similar type of rule, I'm going to write it all in one line, of the sum of two functions or the difference of two functions, that's the same as taking the individual derivatives. So taking the derivative of f at x, taking the derivative of g of x, and then adding those two together or subtracting those two. Okay. And then lastly, we have the constant rule. Okay. Constant multiple rule that says if I take the derivative of a constant times any function, I can just remove the constant from the derivative and multiply it by the derivative of the function. Okay, so here we already saw the examples. For number 1, we saw that the derivative of x to the 1/2 was equal to 1/2 x to the negative 1/2. We saw we're taking the derivative of e to the x plus sine x. That's the same as the derivative of e to the x all alone plus the derivative of sine x all alone. So e to the x plus cos x. And lastly, if I have the derivative of here, let's take another example. Let's say I have the derivative of 5 times cos x. Well, what does that tell me? I can take my constant and multiply it by the derivative of cos x. Okay, so 5 times negative sine x. Okay, of course you can simplify that. Okay, any questions on any of this? Okay, so I still see Jalen Phillips has their hand up. Any question yet or? No? Okay. So why don't I give you a few examples that I want you to try to work on, and then we'll take them up. All right. So if you can take down these exercises. Okay. So here, find f prime of x. So find the derivative. So the first one here is, let's see if we can use this to find the derivative of any polynomial. So let me say 4x cubed minus 2x squared plus 3x plus 5. Okay, I want you to try that one. Okay, then take the derivative of this function here. So let's say the cube root of x plus 7x squared. Okay, and let's start with those. All right, So apply all your rules that we have here, okay, to determine these derivatives. All right, let me give you about, say 3-4 minutes to work on that. All right, and if you have a question, you can just let me know. All right, so let's take a look at these examples. Okay, so for this first one, I'm going to write this out in really, a lot of detail. Normally, I would not write this much detail because you're going to start to see that you can do these very quickly. In fact, some of you who already know how to take these derivatives know that it can be very quick. So what I'm going to do is I'm going to describe how I would just do it in my head, but I'm going to write it down a little more with a little more detail. So here, when I look at 4x cubed, well, I know that 4 is just a constant, so it's just going to multiply the derivative of x cubed, and the derivative of x cubed is 3x squared. So that 3 is going to come down, multiply the 4, give me 12, x, and that goes down by 1 squared. But if I want to show that I'm using the rules, well, I'm going to first split it up. I've got subtractions and additions, so I'm going to split them up into individual derivatives. And here, because I have a constant, I'm going to use my constant multiple rule. So this is equal to 4 times the derivative of x cubed. Then minus, here I have another constant 2 times the derivative of x squared. Plus, here's another constant, 3 times the derivative of x. Oops, 3 times, sorry about that, the derivative of x. And then plus, well, I just have the derivative of this constant here, 5. And so now, 4 times 3x squared, I'm applying my power rule. Now, minus 2 times, I'm going to apply my power rule again, 2x. Here, plus 3 times the derivative of x is just 1. And now, well, wait a minute. What's the derivative of 5? Because 5, what kind of function would that be? That would just be a horizontal line passing through 5. What's the derivative of just a constant? What is the rate of change of a horizontal line? Yeah, there you
Zero.
go. Exactly. It would just be 0. So we can actually add this to our list of rules. Okay. You might have seen this before, but here you can add that the derivative of any constant is just equal to 0, no matter what it is, because a constant just represents a horizontal line. If I were to graph it as a function, and of course, the slope of a horizontal line is just 0, so that's going to be 0. So now I can give my final answer, 12x squared minus 4x plus 3, and then of course the plus 0, and there's my derivative. Okay, now of course, like I said, if you already know this, you know that very soon you're going to go from this step straight to that step. Okay, but now can you see that by having our rules here, now adding in the fourth one for the derivative of a constant, we realize that, hey, we can now take the derivative of any polynomial. And that's good. Polynomials are very important functions. So now we know we can find their rates of change anytime we want. This one here, again, if I'm finding f prime of x, so I'm going to take the derivative of the individual functions and then add them. Now, of course, when I'm taking this derivative in my head, like I said, you're going to do this without having to write it down eventually. But at first, you might want to write this down. And what is x to the cube root of x? Who's going to remind us what the cube root of x looks like? Yeah, looks like somebody has. So what's just the cube root of x? Let's remind everybody how we can represent the cube root of x. Yeah, x to the 1/3, okay? Which is perfect because it means I can use my power rule, okay? And of course this plus 7 times the derivative of x squared. Okay, so here we have 1/3 x to the negative 1/3 minus 1. So 1/3 minus 3/3, so negative 2/3. And then finally 7 times the derivative of x squared is 2x. And so now we can clean this up a little, okay? This will go into the denominator, so it'll be 1/3x to the 2/3, and then plus 14x, okay? And there you go. And now we're starting to see that we can start taking the derivative of a lot of very important functions, all right? So before we move on to the next topic, okay, I want to ask you something, because in the previous unit, you would have learned the derivative of, say, 3 to the x, okay, of an exponential function, and you would have found that that's equal to 3 to the x ln 3. Ln 3 is just a constant. Whereas now, when I take the derivative of x cubed, why isn't it following the same pattern? Notice here, I'm taking the derivative of a power in both of these instances. Why are we getting such vastly different answers? The degree of this cubic, hey, is just this quadratic. Yet the degree of this exponential function is another exponential function. So who can convince me why it makes perfect sense that these rules should be so different? It'd be great if somebody can open their microphone for that. So why should we not be surprised that these rules are so different? Anybody want to give a stab at it? Because it is good to kind of understand sort of why two functions that have a lot in common, they both involve a power, a base and an exponent, yet they have completely different
The X is on the power.
Yeah. Yeah, that's exactly it. It makes all the difference that here the variables in the base and here the variables in the exponent. okay, it produces a completely different function. You know that x cubed, okay, has, it's a polynomial. On one side, it goes to positive infinity, the other side to negative infinity. Okay, and all polynomials have that end behavior. They always go to one of the infinities on either side, whereas 3 to the x is a completely different function. It's a function that's always positive, it's never negative at all, has a horizontal asymptote on one side, but approaches positive infinity on the other side. That even though they have a similar look, they are very, very different functions, okay, with their own properties. So the fact that here the exponent is the one with the variable makes it an exponential function, follows the rule of derivatives of exponential functions, whereas here the variable's in the base, which means its polynomial function follows the rules of these derivatives of power functions, where the base is variable, but the exponent is some fixed number. All right, so make sure you're not interchanging these rules. Make sure you're very clear that the, exponent coming down and bringing down the exponent by 1 only works when you're taking the derivative of a power function, meaning the variable is in the base, whereas here the variable is in the exponent. All right. So, I think what we're going to do, I think we have to have a break at 7:15. Okay. So, what I'm going to have you do, because I know technically I'm supposed to be following the bright space. So I know I'm not completely following that, but what I would like to do is maybe just have you take a look at the content. Okay. And let's see about some of the questions that you can answer. Okay, so here we're doing Unit 5, properties of derivatives. Okay, so I just want you to have a quick run through. Okay, so you don't have to do the exercises because we've done most of them. Okay, but just have a quick look at the the material, okay? And there's a couple of questions I will give you from here. Okay, you know what? Actually, I think I know what I'm going to have you do. Because so far, all the examples we've looked at that use the power rule, so if you think back to what we did earlier, we did here, what did we do? We did x squared and we did x cubed, okay? So what I want to give you here is another example, okay, to show that the power rule doesn't just work for these nice positive integers, okay? So what I'm going to give you as an example here is I want you to find, using the limit definition, so using limit definition, okay, I want you to find the derivative of 1 over x, and I want you to find the derivative of 1 over x squared. Okay, so using that limit definition, f at prime at x is equal to limit as h approaches 0 of f at x plus h minus f at x all over h. Okay, oh sorry, this is supposed to be 1 over x squared. Okay, now the difference here is you're going to have to use your knowledge of rational expressions. Okay, so in the previous examples, we were just expanding polynomials and we were able to determine the derivatives by just using things like expanding and factoring. Here, I'm going to give you a little bit of a tip. Because you're going to be dealing with rational expressions, you're going to have to add and subtract rational expressions to solve this here. But these are I would say fairly straightforward, but I'll give you some time to work on that. We'll take them up and then that'll probably be the last thing we do before our break. All right. So if you have any questions, please ask. Otherwise, I'll give you about 4 or 5 minutes to work on these two. Okay?
I have a question.
Yeah.
How this is kind of like a side question, but like
Yep.
I was wondering, like, how important is it to know how we got to the conclusion of the rules? Like, can I just like search up the rule on the internet, or do I actually need to know how we got to the conclusion?
So in the end, what you're going to be using, certainly in the rest of the course, is just applying the rules, okay? In terms of understanding where they come from, well, how important that is maybe might depend on, what you might choose to study later on, So if you're going to be doing maybe a more technical degree, or so maybe not, maybe technical is the wrong word, but if you're going to be doing a more academic degree where they're going to be doing things like proofs in their math courses, then yeah, it is good because this kind of introduces you to the idea of proving something instead of just kind of looking at patterns. So from that is, if you're going to do something that's a more applied degree where you're going to, calculus is just going to be used as a tool, then, probably not that important. So that's the best answer I could give is, how
Thank you.
important it is depends on what you're going to choose to study. But
Thank you.
my
Makes
view is,
sense.
yeah, but it's always nice to kind of see how math is done. Sometimes at least, for me, it makes me feel better that I kind of see that somebody didn't just, pull it out of their ear and says, okay, here it works, just apply it. It's kind of nice to see that things actually work. Yeah, like art, that's a really nice one. I have said on many times that mathematics is a lot like art. Okay, so let me give you a bit of time to work on this here. Okay, so while you keep working on this, I'm just going to start writing out the solution to the first one, just in case anybody's struggling, they can follow along. Okay, but the rest of you, just try to finish those off in the next couple of minutes if you can. Yeah, I'm just setting up the problem. So as people are working on it, just so that I can save myself a bit of time. So I'm going to give you, you have about another, oh, actually it's about time. Or it's 7:06. I want to give you to 7:06. Okay. So let's take a look at what I did here. Okay. Well, I just remember use my formula. So wherever I see, you know, an X, I have to put in X plus H minus 1 over X. Okay. Except now the algebra I need to do is to work with these rational expressions. So this is, you know, good review of working with rational expressions. So sometimes you have to work with them. And so what I needed to do is find a common denominator. So my common denominator is X times X plus H. So here, if I multiply the denominator by X, I gotta do the numerator. Here I multiply the denominator by X plus H, so I do that to the numerator. And now I can subtract these two. Now, if you're doing a question like this, remember when you're doing the subtraction, you're subtracting the whole numerator. So please don't forget to put brackets, otherwise you'll get a sign error. Okay, and since I'm dividing this whole thing by h, well, we know dividing by h is the same as multiplying by 1 over h. Okay, because again, I want to try to simplify this as much as possible. Okay, so let's see what happens. Well, here, x minus x, that cancels out. So I just have the minus h. Okay, that's why it was important to have the brackets here. And what are we left with? Well, we have h times x plus h. Okay, and look what happens, as has happened in every other case. The h's cancel out. So I'm just left with a -1 in the numerator. And now in the denominator, I can evaluate the limit because x is not affected by h approaching 0. And here as h approaches 0, well, this whole thing just approaches x. So this approaches 1 over x times x, or -1 over x squared. Okay. Now, does this match our rule? Because we can also write, I don't think I'm going to have time to do this one here, so I'll leave it as an exercise if you want to work on it. I'm just looking at the time. If we look at our rule, we know that we can rewrite 1 over x as x to the -1. And so now we can use our power rule. And what does our power rule say? Well, the exponent becomes the coefficient, and the exponent goes down by 1, so -1 minus 1 is just -2. And look what we have, -1 over x squared. Exactly what we got here. So what this tells us is that the power rule that we had come up with, okay, doesn't just work for nice positive exponents. It tells us that this power rule works for any exponent, okay? As long as it's the base that's the variable, okay? So, any questions on that? No? Okay. So, one thing you may have noticed is here I'm talking about the derivatives of sums, okay? So I know that the derivative of, you know, f at x plus g of x is the sum of the individual derivatives. Okay, that's great. And I know the difference, the derivative of difference, is the difference of the individual derivatives. So what would be the natural next thing to look at? Who can tell me what would be the natural next thing to look at? Well, if you've done addition, if you've done subtraction, what should be our next investigation? Any ideas? Yeah, why don't we look at the derivatives of multiplications? Exactly. So now, hey, if the world was the, you know, the most perfect of all worlds, what would you expect the derivative of a product to be equal to? Okay, So here we had the derivative of the sum was the sum of the individual derivatives. So what would you expect if everything worked out perfectly? What would you expect the derivative of a product to be equal to? Any ideas? You know, imagine we lived in the easiest possible world. What
It
would
would
it take?
be equal to the derivative of f of x times the derivative of g of x.
Yeah, wouldn't that be fantastic? And it would make perfect sense, right? Because, hey, if the derivative of the sum is the sum of the individual derivatives, then, you know, why shouldn't the derivative of a product just be equal to the product of the individual derivatives? And in fact, let's take it another step further. What if we were taking the derivative of the quotient of two functions? Wouldn't it be great if that was equal to the derivative of the numerator function divided by the derivative of the denominator function? That would be fantastic, wouldn't it? Now, I hope based on the tone of my voice, you're probably guessing that these things are not true. Okay? And this is as nice a rule as you can get. It would have been fantastic if these rules were true. Unfortunately, they're not. Okay? So before we go, what I want you to do, the last thing I want you to do is I want you to come up with an example, okay, to prove that this is not true. Now, that's the thing about proving that something is not true. You just have to find one example where it doesn't work. Okay? So you can take maybe even some examples that we've already seen here, okay, and see if you can show me that these rules, as nice as they would be to be true, are not true. Okay? So take the last couple of minutes to work on that and try to come up with examples to prove that these don't work as much as we would like them to work. It's going to be very sad that they don't work, but you know, that's what it is. Okay, so take 2 minutes to look at that. Okay, so notice what I did is I took one of the examples we already know the answer to, because obviously x times x is x squared. So I know that this derivative has to be equal to 2x. We've already established that. In fact, we even proved it. Okay, so let's see now what happens when I take the derivatives of the individual functions. Well, what's the derivative of x? That's g equal to 1. And what's the derivative of x? That's equal to 1. And of course, 1 times 1 is equal to 1. So are these two things equal to each other? And the answer is no, they're not equal to each other. So what this shows is that the derivative of a product is not equal to the product of the individual derivatives. Okay? And you can come up with a similar example for derivatives of quotients. All right. So what we're going to have to do is we're going to have to try to find, hopefully, a rule that does give us the derivatives of exponential function, products of functions. Because remember, what we're trying to do is we're trying to avoid having to use the limit definition every time we want to find a derivative. We want to be able to find the derivative of any function, even if it's a combination of real ugly functions put together. We want to be able to do that without having to use the limit definition. Okay, so I think if I'm not mistaken, the break is at 7:15, I believe. Or is it at 7:30? Now I'm starting to question myself. Can somebody confirm whether the break is at let's see. Oh, the break is at 7:30. Okay, so maybe we'll just go on. Do we prefer taking the break now, or do we want to wait till 7:30? Oh, it's usually flexible. Okay, this is kind of a nice time to, oh, some people say continue. Okay. Well, I'm going to continue just a little bit, okay? Because this is kind of a nice time to take a break. So maybe what we can do is let's sort of look at an example for quotients. Did anybody come up with, can somebody give me an example they used for a quotient? Any suggestions here as to what I might use to show that the derivative of a quotient? So then look here, look how I use something very, very simple. Okay, x squared over x. All right, let's check that. So here, if I take the derivative of x squared over x, which of course we know if I simplify is the derivative of x, which is 1. And so now on the other side, let's rewrite it as the quotient of the individual derivatives. So derivative of x squared over the derivative of x. And we look here in the numerator, the derivative of x squared is 2x. The derivative of x is just 1. And clearly, these two things are not equal to each other. Okay? So this shows that these very nice rules that might have worked for addition and subtraction don't work at all for multiplication and division. All right, so our goal now is a -1. Maxwell, can you, what were you gonna bring up there? Okay, -12x squared minus 4x plus 3. Multiplication.
Oh, that was earlier. I just I worked ahead.
Okay, is that for an earlier example or?
Yeah, that was the paper we where we had to work individually for like 3 minutes, and
Oh,
I
okay.
I put in
Okay.
the answer. Yeah.
Yeah, perfect. So let's take a look. We'll just go check. That was the one we took up before. Yeah, and that's exactly the answer we had got. Perfect. Okay, so let's give you a couple of more examples and then we'll go take a break. So, because I do want to leave enough time for enough time to put on the product rule. In fact, if you want, I'm even happy to do the quotient rule. If you want to do that, we can do that later on. All right, so let's give you a couple of more examples to work on. All right, so Okay, I want you to do these two examples here. Okay, I'll give you 3 minutes to finish those off. Okay. All right, so hopefully you're able to have enough time there to do that. So here, notice I've got this root function, I've got this reciprocal function. So definitely the first thing I want to do is rewrite those expressions in exponent form. So this is x to the, well, exponent 5 and root 3 is like 1/3. So that's x to the 5/3. And here, 4x to the 7 plus here, instead of writing this as 2 over x cubed, I can write it as 2 times x to the -3. And then, of course, here I have the minus pi to the 4. Okay. And so now I have everything in the format that allows me to use my form, my rules. So here, and notice now I'm not going to write it with as much detail. So here, the power becomes my coefficient, and 5 over 3 minus 1. So it's like 5 over 3 minus 3 over 3 leaves me with 2 over 3. And here minus 4 is just a constant. And the derivative of x to the 7 is 7x to the 6. Okay. And here plus 2 times. Well, what's the derivative of x to the negative 3? It's just a power. So this is just going to be negative 3 x to the, well, negative 3 minus 1 is negative 4. Okay. And what's the derivative of pi to the 4? So who can give me, finish it off? Who can give me that one? What would the derivative of pi to the 4 be equal to? Darn, I was hoping somebody was going to fall for my trap here. Okay. And this is where you want to be careful. Okay. I put this on every test that I give. And, you know, at least a third of the people write 4 pi cubed. But of course, pi to the 4 is just a constant because pi is a number that I take it to the power 4, doesn't make it a function. It's just another number. So this is just 0. Okay. And very often you might be asked not even to simplify, and you can just leave it as is, or you can, you know, start to simplify this a bit. So here, what is this? Minus 28x to the 6 minus 6 over x to the 4. And there you go. And you can usually leave the answer as that. All right. Now here, you might have said, hey, Tony, wait a minute. I thought you said we still don't have a quotient rule because I can't just take the derivative of the numerator and the derivative of the denominator. But how could you have solved this problem still using the tools that you had? What would have been the first step here? So what?
You use
Yeah.
product rule.
What's that?
You use product rule, and then
Well,
so
we still don't have, remember, we still don't officially have a product rule. You know, technically we don't know what the product rule is. So
I mean, you could bring the x cubed. I mean squared, and then bring it to the top, and just have it negative. Just have x negative 2, and
yeah.
then just use the product rule on one, and you group the x negative 2 as one term, and the other term is the quadratic equation on the top, and then you
Yeah.
just use product rule on that.
Yeah, except remember, we haven't technically, so maybe you know the product rule, but we don't necessarily know that yet. So I want to avoid using a quotient rule. I want to avoid using the product rule because we haven't technically learned it yet. Okay, so I see that you can factor out the x squared from the numerator, and there you go. What you see is that you can simplify this. Okay, so by the way, what you mentioned wasn't wrong, but I don't want to use a rule that we haven't established yet. But what you can do is either factor out the x squared from the numerator, or, you know, when you're dividing a monomial, you're just dividing it to each term. Okay, it's just a distribution. It's like distributing 1 over x squared. So here we can simplify this. This just becomes the derivative of 3. This x to the 5th divided by x squared is just 3x cubed. Then this is 5x squared. And then minus x squared divided by x squared is just 1. And now we can take the derivative in our usual way. Okay, so sometimes it's worth simplifying first before taking the derivative. So that's sort of the lesson here, is that if you see something that can be easily simplified into a simpler expression, it makes way more sense to simplify first and then take the derivative. Because now this is really easy. 3 times 3x squared is just 9x squared. Here, 5 times 2x, 10x. And you see how now I'm doing it all in one step. That slowly you get comfortable doing it in one step. And then here, oh, I don't need the bracket. And then of course the derivative of 1 is just equal to 0. And there's your derivative. Okay, so here it was about rewriting it in the proper form that allows you to take to use the derivative properties. And then here it's the idea that if there's some simple algebra you can do then better to do that first and then take the derivative on the simpler expression. Okay, so we're at 7:30. Let's take a break. So we'll take a 15-minute break. We'll go till 7:46 because it just turned to 7:31. Okay, so get a good break and we'll see each other in a little bit. All right.